the screen, we're going to look at this graph to cover what we need to know about changes of state. Okay, so remember right back at the start of this topic, and we talked about solids and liquids and gases. Okay, solids, liquids, gases. Make sure you're confident about describing how these particles are arranged. So remember, in a solid, you've got this regular arrangement. The solid particles are fixed in position, but they're just vibrating a little bit around a fixed point. Okay? And when they melt and become a liquid, those particles are still touching close together, but can swap places. And then we add more energy. Liquids boil and turn into a gas, and that's where the particles have really big spaces between them and moving around randomly. Okay, so gases will always fill the container that they're in. Liquids and solids will both have a fixed volume, but the liquids take the shape of their container, whereas solids keep their own shape. All right. Now the graph shows the temperature change. So if you imagine we started down here with a solid that was cold, and we warmed up the solid, and it's getting warmer and warmer and warmer. Whilst this is happening, the particles are vibrating more, and the energy input is increasing their kinetic energy. So when the temperature goes up of a substance, the kinetic energy of the particles goes up. All right. Now, when it gets to the point where these particles have reached sufficient temperature to start to move away from each other, you can see what happens here, where the temperature doesn't change. So that's quite weird. All right. So the key idea here is, if we were warming up an ice cube, let's say we got an ice cube out of the freezer at -10, and we left it on the side, it would warm up, warm up, warm up. It's ice, it's ice, it's ice. And when it got to 0 degrees C, then the particles would start to move away and change positions, and we say that the ice is melting. During that time, all of the energy is going into the change of state. And the state change is related to the potential energy, of the particles in terms of where they are. So a key fact to memorize: when something changes state, the temperature does not change until the state of change is finished. So in this part of the graph here, this horizontal line, you'd have a mixture of solid ice and liquid water, and only when all of the ice had melted at this point here would the liquid start to warm up and gain kinetic energy again. All right, so we talk more about this in physics, okay, but the total amount of energy of these particles, which we'd say is the internal energy, is equal to their kinetic energy, which is about their temperature, and their potential energy, which is to do with where they are relative to each other. So you can see you've got two characteristic flat sections on this graph where the state changes happen. Exactly the same thing would happen if we kept heating up liquid water, hot water, hotter, 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 boiling 100 degrees C. The water would stay at 100 degrees C until every bit of it had boiled and turned into a gas. So only steam, water in the form of steam, can be hotter than 100 degrees C, but liquid water can never be hotter than 100 degrees C. Okay, and whatever your substance was, this temperature for water, it would be 100 degrees C, and this temperature for water, it would be 0 degrees C, are the state change temperatures. So you can say, you'd be correct to say that ice melts at 0 and water freezes at 0. You'd be correct to say that liquid water boils at 100 and water in the form of a gas condenses at 100. Okay, so the flat point on the graph, that is really, really important idea, and that is referred to as latent heat. So even though you're putting in energy, the particles are not getting hotter in terms of their temperature, but all of that energy you're adding is going into doing the state change. Key facts: an ionic bond is between a metal, in this case sodium, and a non-metal. So if you've got a compound made of a metal that has joined to a non-metal, that compound is joined together with an ionic bond. Remember our rules: metals lose electrons. Losing is positive. Metals make positive ions. Okay, and the opposite is true for non-metals. So in our diagram here, we've shown what happens in the ionic bond between sodium and fluorine. Only the outermost shell of electrons has been shown. Here's the electron arrangement of sodium. Here's the electron arrangement of fluorine. When they bond, the sodium wants to end up with a full shell, and the easiest way to do that is to give away its electron and give it to the fluorine. Notice what happens. That extra electron has made fluorine have a full shell, so we now call it fluoride, and it's happy because it's stable. And sodium has lost that single electron, so now its second shell remains, and that one is already full. So again, the sodium ion gets a full shell and is stable. Losing is positive, gaining is negative, opposite charges attract, and remember we call that an electrostatic attraction. So an ionic bond is made when a metal gives away its outermost electrons to a non-metal. Metals always make positive ions, non-metals always make negative ions, and opposite charges attract. All right, let's link that to our periodic table. Okay, so here I've just shown the first 10 elements. Okay, and remember the rows, the period represents how many electron shells there are. So this is the first shell of electron. Hydrogen's got 1, helium's got 2. This is full, so it's already stable. And then if we go back to the start of the second row, lithium is number 3. It's got 1 electron in its outer shell, beryllium 2, and we're filling up that shell of electrons as we go across the second period until we get to neon, which has got 8 in its outer shell. It's stable as well. Linking that to the ions, okay, lithium and beryllium, okay, are metals. They give away their outermost electrons. If I lose one, losing is positive, I'm going to be 1 plus. If I lose 2, I'll be 2 plus. Lose 3, 3 plus. Okay? I'm going to skip carbon because carbon doesn't make ions very often. And we're going to go to fluorine in group 7. It needs to gain 1. Okay? To make 8. Oxygen needs to gain 2 to make 8. And nitrogen needs to gain 3 to make 8. And finally, let's link that to their group numbers, because remember, the group number is the same as the number of electrons in the outer shell. Lithium is group 1, beryllium group 2, boron group 3, group 4, group 5, group 6, group 7, and we call this last column group 0. There's no gaps for any electrons. They're not going to make ions. They are stable. They don't need to join with other stuff to become stable. Okay? So we could say that the least stable groups are group 1 and group 7. They are the most reactive metals are in group 1 and the most reactive non-metals are in group 7. All right? And when these ions join together, they join up and make these giant ionic lattice of many, many ions joined together. And if you get diagrams like this in the test, we can look at the number of particles, and you can see here that this is sodium joined to chloride, so we know that this diagram represents the structure, the ionic bonding in sodium chloride. And if we counted them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, there is a ratio of one of those to one of those. Yeah, the formula is 1 sodium to 1 chlorine. And that is because sodium ions are 1 plus and chloride ions are 1 minus. Okay, so a ratio of 1 to 1 cancels them out. Okay, if we took magnesium, which was 2 plus, and we wanted to join it to chloride, which is 1 minus, you can see here that for every 1 magnesium, you're going to need 2 chlorides to cancel out the charge. The formula for magnesium chloride is for every 1 magnesium, you need 2 chlorides. Okay? So we can link the structure to the formula. Okay. We're talking about covalent bonds. All right, so our next type of bonding, covalent. All right, covalent bonds are shown by diagrams like this. And a covalent bond equals a shared pair of electrons. Here, okay, in the overlappy bit. So this diagram is showing water molecules, H2O. We can see in the diagram that the hydrogen, yeah, whose electrons are represented by this plus, are sharing their electron with oxygen, whose electrons are represented by these dots, and oxygen, which is in group 6, okay, I can tell it's in group 6 because there's 1, 2, 3, 4, 5, 6 electrons that belong to oxygen. It's in group 6. So if it makes 2 bonds, it gets up to 8. And remember, 8 is the magic number to fill up that energy level. 1, 2, 3, 4, 5, 6, 7, 8. Hydrogen has got 1 electron. So if it gets 1 by sharing with the oxygen, it fills up its only energy level with the 2 electrons. That's the magic number for filling up the single first shell in hydrogen. So we could show that like this. Hydrogen makes a covalent bond to oxygen, and oxygen makes another covalent bond to hydrogen. There's our water molecule. Okay, now that is it. These covalent bonds are strong. Okay, that means they take a lot of energy to break them, but individual molecules of this covalent structure don't have any charges, so they're not attracting each other, so they're not giant, and so they're going to have low melting and boiling points. Remember, when we're talking about these simple molecules like water, like methane, like carbon dioxide, okay, we explain the fact that they're a gas or a liquid at room temperature by talking about the fact that the forces between molecules, intermolecular forces, don't hold them together very strongly, and so it's easy to separate them by melting and boiling them. Their melting and boiling points are low. Okay, so when we talk about covalent bonds, remember, never say that they're weak, they're strong. But if you've only got a few, then the molecule that it makes is probably going to be a gas or a low boiling point liquid. Right? But the strong covalent bonds are also present in giant structures that we talked about, like diamonds and graphite. Okay? And these are 2 forms of the same element. They're both forms of carbon. Okay? So the diamond is pure carbon and the graphite is pure carbon, and both of these are examples of giant covalent structures. The carbon atoms in the diamond make 4 bonds, which is the maximum number for group 4 carbon to make. Whereas in graphite, you can see these hexagonal discs make layers of carbon atoms where the carbon only makes 3 bonds, and that gives graphite its unusual property as a non-metal of being able to conduct electricity when it's solid. Okay, so the spare electron from each carbon is buzzing around within the structure of the graphite, and that explains why the graphite is the odd one out in the non-metal world. It conducts electricity when it's a solid, just like a metal. All right, so if we're talking about a solid that conducts electricity, it's likely to be a metal, but it could be graphite. Now, both of these structures are giant covalent, so they have many strong bonds, and therefore their melting points are going to be very high. All right, the diamond is very, very hard with a very high melting point. The graphite has a high melting point, but because, can you see these dotted lines here are just weak forces between the layers, that explains why graphite, although it's got a high melting point, is also slippery. Okay, so graphite is in your pencil. When you write with your pencil, the pencil slides across the page, and as it slides across the page, these weak forces between the layers of the graphite are easy to overcome, and the layers of graphite are left behind on your page. Okay, so graphite is softer than diamond because the layers of carbon atoms will slide over each other. Okay, only these little free electrons are holding the layers together, buzzing around, and that also explains why it conducts electricity. Okay, hopefully this is sounding familiar to you. Right, let's stick with our conducting electricity and talk about metals, our last type of bonding, the metallic bond. The metallic bond, what holds metals together? Okay, metals are solid, apart from mercury, a regular arrangement of particles. But in a metal, in all metals, the outermost electrons, they are delocalized. That means they're free to move. So just like the graphite, all metals are good at conducting electricity when they're solid. Okay? The free electrons can move through the metal structure, carrying charge. That's what conducting electricity is. Okay? So because metals are held together, we talk about a sea of delocalized electrons. This sea of delocalized electrons means that the particles, which we should refer to as metal ions, but metal particles can move around each other. That's why metals can be bent. Metals are malleable. We can bend them into shape. We can bend them into shape because the metal particles can swap places with each other because they're not held rigidly in place. They're sort of suspended in this sea of electron cloud, and that means they can move around each other. Okay? Metals bend without breaking. They're not brittle. Sometimes that's a problem, and pure metals can be really soft. Okay? So sometimes we add stuff to make pure metals harder. Do you remember we talked about gold as an example of an alloy? Key word. Yeah? An alloy is a mixture of metals. That mixture of metals means that the nice neat rows of metal atoms are disrupted by a different sized particle. Okay, so these bigger atoms here mess up the nice neat layers. The layers can't slide. Okay, and therefore alloys are harder than pure metals. So hardness in a metal depends on how easily the layers of metal slide over each other. So we think of very soft metals like gold and lead. The atoms slide really easily over each other. Okay? If you alloy your metal, for example, we might mix some tin with our lead and make solder, which maybe you've used in technology, and that is a harder material, an alloy. All right. Finally, whilst we're talking about conducting electricity, make sure you're happy with the fact that if you have an ionic compound and you melt it or you dissolve it in water, that the ions will be able to swap places and move around. And because the ions are charged, sorry folks, my computer overheated again. Let me share my screen for the last little bit.
We lost you for a bit.
Yeah, I know. Sorry, my computer overheated and turned itself off. I'm putting too much demand on it, I think. So we were just saying, finally, just remember that if you melt or dissolve ionic compounds, they will conduct electricity because you've got charged particles, but they can only move if you melt them or dissolve them. Okay, so if something is conducting electricity and it's a solid, it has to be a metal, or it could be graphite. Those are the only possibilities. Whereas if something is conducting electricity because it's a liquid, that means it's been melted, or if it's a solution, it's been dissolved, that means it could be an ionic compound. All right, but obviously it has to be very hot to melt these things because they're giant structures. Okay.